My name is Jamaica Marshall, and I am your session host and the Shadow the Scientist Programs Manager. I am here live in the Subaru Telescope control room for tonight's session, Astronomy Night with the C3V0 team, hunting giants at the edge of the universe. That's with Mr. Joel Diamond, Mr. Finn Giddings, Dr. Roy Gal, and Dr. Brian Lemaux. Now, Shadow the Scientist is an initiative that's brought to you by a fantastic team at the University of California, Santa Cruz. Now, for tonight's session, as I said, I'm here in Hilo, Hawaii at the Subaru Telescope Base Facility. And as you can see, observations are already underway. So to get us started, I'd like to introduce one of our science hosts for this evening, Dr. Brian Lemaux. Brian.
Hey, Jamaica.
Hey.
Yay, we're in the same room. Hey, where are you?
Oh, there you are. Here I am.
Yeah, thank you. Thank you very much for everybody to be here. And yeah, we're in the Subaru base facility. We're in Hilo, Hawaii tonight. We are observing on the Subaru telescope, which is an 8.2 meter telescope near the summit of Maunakea, as Jamaica said. We are currently taking observations. Right now it's 9:37 at night, Hawaii Aleutian Standard Time. We're actively taking observations at the moment, so I'm going to kind of move back and forth between different cameras and different screens. As you can see here, we have 15 different screens in this room, and some of them have about 15 different subscreens. So we're keeping an eye on a lot of different elements of the observing process. I'm joined here by Finn Giddings, who's a graduate student at UH Manoa, and Joel Diamond, who's a visiting undergraduate student for the University of Charleston. And on the summit, we have Kentaro Aoki and one of the telescope operators for the Subaru telescope. And then we have Roy Gal joining us from Oahu from his kitchen table. So this is truly an endeavor of a lot of different places. Sorry, Kentaro, did you say something?
Hello.
Hello, Kentaro.
Hi. How are you?
Doing well, thank you. Thank you for allowing us to shadow you and your colleagues as you all are doing amazing things tonight.
So that's Kentaro Aoki, that's joining us from the summit. They're actually in the Subaru telescope facility up there. They're moving the telescope. They're helping us with the observation process. They're much more knowledgeable about the telescope the structure, the optics, the underlying instruments than we are. And we're here as a visiting science team taking observations with their telescope. So as you heard in the background, we are taking exposures at the moment. We're doing imaging, and we'll talk about that a bit later. And we're actually about, so we're taking rapid exposures, and rapid, at least for me, is about 3 minutes at a time. So there's telescopes and instruments around the world that take images on picosecond timescales, 10 to the minus 15 second timescales. And so not as rapid as that, but pretty rapid for me. So we're observing in the near infrared this evening. We're observing at about 2.3 microns. And so the sky is very bright at these wavelengths because we're on the ground. And the atmosphere shines, and there's heat, and heat is thermal radiation. And so we have to take a lot of exposures and combine them all together. So I'm gonna pass to Roy to talk about a little bit of the science goals for this evening, and then we can come back to the telescope and some of the observations that we're actually currently taking.
Welcome, Roy.
Aloha, everyone. Thanks for joining in our shadow session. So what I'm going to do is share my screen and talk a little bit about our project and in general, and more specifically about what we are targeting tonight. And I'm going to try to bring it to a level that hopefully will be understandable to all of our audience. And if you have any questions, please go ahead and put them in the chat, or if there's not too many people online, you can even just, I don't know if it's allowed, you can unmute and just ask. So our team is almost Star Wars named. Our project, I should say, is C3VO, not C3PO. And it is an acronym because astronomers love acronyms. And beyond being an acronym, it's an acronym that contains two other acronyms. So it's the most awesome acronym in all of astronomy, perhaps. So it stands for Charting Cluster Construction with VUDS and ORELSE. And there's a lot of words in there. But VUDS and ORELSE are other surveys of the sky looking at clusters of galaxies. And the clusters that we talk about here are galaxy clusters. So in this image, in this kind of thing that looks like soap film or bubbles or whatever, it's actually a simulation of a chunk of the universe made in a computer.
Yeah, Kendaro's just starting the next set of others. Yeah.
Yeah, Brian, ready to do again focusing.
So after this set of dithers, or you want to do focus now?
Yeah, focus now. And move to SWC later.
Okay, sounds good.
All right, so you could hear some of the science team, Brian, talking with some of the observing the Subaru telescope staff as they're planning to move to a different target and refocus the telescope to make sure we're getting the sharpest images possible. Okay, so back to this image that doesn't look much like an astronomical image.
Let me do a field check for this one, probably.
A map of a large part of the universe in a computer. And every tiny little dot you could think of as a galaxy. And the dark areas don't have galaxies and the bright areas do. And you can see the universe isn't random. The galaxies aren't randomly distributed. They form in these walls and filaments, and where those intersect, you get clusters of galaxies with thousands of galaxies in them. And when you look at those clusters of galaxies today, they have lots and lots of galaxies. Those galaxies look like they've used up all their gas. They're not really making stars anymore. But as we look back in time, those clusters are still in the process of formation. Those galaxies are falling in via gravity and changing. And we're trying to understand what happens in that growth process and what happens to galaxies. And we do that by looking back in time, sort of just like a paleontologist would dig deeper and deeper to see older and older dinosaur fossils and figure out how they evolved from one type of dinosaur to the next. So in the project that we're doing now, we're looking at galaxy clusters at distances that correspond to look back times of about, let's say, 10 billion years. So we're looking back most of the age of the universe, about 3/4 of the age of the universe. All right, so before I talk about the science, the observations that we're doing today, I'm going to talk about why we chose the targets that we are looking at today. And we didn't actually choose these targets in the first place. We have some colleagues who look at the universe and map it a different way than we do, using something called Lyman alpha tomography.
That's right.
And that is a way of mapping the universe using backlights rather than the light of the galaxies themselves. So I'm going to explain what this means. So,
yeah, okay.
Yeah, much better. This is optical thing.
Yep, exactly. Yeah. So that's great.
So let's move to SWC, correct?
That's correct. Yeah. Yeah. So just for
SWC. Yep.
Yep. Perfect. Yeah. Yeah. We'll do the normal 23 dither pattern if everything goes well.
Yeah.
So yeah, just yeah. So again, we're actively taking observations here, and we just did a focus, and our focus is the resolution has increased quite a bit over the course of the night. In the beginning of the night, we were a little bit disappointed because it was below average for Maunakea. It's above average for almost every other site in the world, but it was below average for Maunakea. But things have improved by almost a factor of 2 now. And we're much, much happier. And we're actually moving to our most like highest scientific leverage field of the entire survey tonight. And in fact, we're moving right now. So we're in a perfect spot because the target that we're looking at is rising. So it's higher up in the sky, so we have to look through less atmosphere. The blurring of the atmosphere and the ground layer is less. And the clouds that were here previously, they were here last night a little bit and a little bit tonight, those have all cleared at the moment. So we're very, very happy astronomers.
Yeah, so the resolution that Brian was talking about is the blurring due to the atmosphere. It's not like our camera or telescope got better, but the atmosphere is blurring the images less, so we're getting a sharper view of the universe. So when you see twinkling stars, that's the atmosphere focusing and defocusing light. That's called seeing in astronomy. And right now we have very good seeing, so the stars are not twinkling very much. All right, let's see if I can go back to my slides here. All right, so to understand the Lyman alpha part of the name of what I was describing as how some of our targets were selected, we need to look at how hydrogen atoms work. So hydrogen atom has a proton and is surrounded by 1 electron. And that electron in quantum physics can have certain specific levels of energy. And it can jump from one energy level to another by absorbing energy. And that could come from atoms bumping together, or it can come from light, a photon, a particle of light, hitting that electron. And if that light has just the right amount of energy, that electron will absorb that photon and jump up to a higher energy level. And then when it gets tired of being at that higher energy level, it wants to relax and go down the ladder of energy levels, and it will release light of that same color. So if there's light passing by this hydrogen atom that doesn't correspond to any of these ladder rung jumps, it just passes right by. The hydrogen atom can only absorb light that has the right energy to jump electrons among these levels, and that's what these arrow diagrams represent. And so in Lyman alpha tomography, what we're using is the fact that these hydrogen atoms along the line of sight to something can absorb light, and the electrons jump up. And when that happens, that specific color of light doesn't make it to our eyes. So one way to think of that is you have something giving off a bunch of light, and in the way you have a cloud of, let's say, hydrogen gas. And if you give off all the colors of light, like the beautiful rainbows that we have here in Hawaii, if you put hydrogen gas between you and the rainbow, then that hydrogen gas will absorb the specific colors of light that correspond to these ladder jumps. In this case, the arrows are shown going down, but for the jumps, they would be going up. Now, the hydrogen gas, when those electrons decide they want to relax, it will also give off the light. And so you can see the light that gets absorbed also gets emitted back out in all different directions. But in our case, for Lyman alpha tomography, what we're interested in is we're looking at faraway galaxies that we actually don't care about. And what we really care about is mapping the structure of the universe via gas. So we need to mix the fact that gas absorbs these specific colors of light with another concept, which is redshift. And that's when a galaxy is moving away from you, the light that it's giving off is shifted due to the expansion of the universe. It looks like the galaxy is moving away from you very fast, but that's really due to the stretching of the fabric of space-time. So if we have hydrogen gas in a laboratory and we looked at it in absorption, we would see these black lines at a specific colors or wavelengths of light. And as you move that galaxy further and if that hydrogen gas is in a galaxy further and further away, those lines get shifted more and more into the red. And that's why we're observing in the near infrared, because we are looking for galaxies that correspond to hydrogen gas that's observed at very large distances from us, where the light that would normally be given off in visible wavelengths gets shifted way into the infrared. All right, so if you are looking for this hydrogen gas, what you do is you look for a backlight a very, very distant galaxy or a quasar or some bright light source, and then you look for the imprint of these clouds of gas along the line of sight, and those will create these absorption lines, these missing colors at different, they'll be in the same pattern as hydrogen absorption, but shifted. It's like a fingerprint, but shifted in wavelength, stretched out. And if you only had one cloud along the line of sight, you'd see one of those fingerprints, but shifted in wavelengths. But if you have multiple clouds, you'll see multiple of those fingerprints overlapping, all shifted different amounts. The pattern, the ratio of the colors of the lines always remains the same for hydrogen, but the exact colors they're at changes due to redshift. So our colleagues in a survey called LATIS have taken advantage of this. So they're looking at hydrogen, this energy transition in hydrogen, which is called Lyman alpha. It's an electron transferring from the first excited energy level down to the relaxed level. That's called Lyman alpha. Okay, so
Right, Kentaro, please.
No problem.
and this happens at this corresponds to high energy light,
Thanks.
in the ultraviolet. But when it's redshifted, it can be seen at more visible wavelengths. So this is the experiment that our colleagues at the LATIS survey have done. They have looked at a bunch of individual background galaxies, taken their spectra, and then looked for absorption from hydrogen gas along the way. And then if there are a bunch of galaxies in the distance that all show absorption of gas at the same redshift, it means that there's a big hydrogen cloud. You can't see that hydrogen cloud because it's very, very diffuse, but you can see its shadow basically imprinted on all these different galaxies. And so and when there's no hydrogen gas, you don't see that shadow. So they're using these shadows of gas to map out where there is hydrogen gas, big, big piles of hydrogen gas in the universe.
Roy?
Yep.
Quick question. When you say shadows, do you mean they're seeing the imprint in the spectra, or do you mean something
Yes.
else? Okay.
Exactly. They're seeing these absorption lines imprinted. You can't see the hydrogen, which is very diffuse and spread out, but you can imagine imagine you have some very thin window screens here and there that you can't see for some reason. But if you have a bunch of flashlights shining in the background, you can see where there is and is not a window screen, because some of those flashlights will look dimmer and some will look brighter. Now that's with our eyes and we're mixing the colors together. But in this case, that's the wavelengths where they seem dimmer corresponds to the redshifts of the distance of that hydrogen gas from us. And if you have a bunch of flashlights, you can start to map out where those window shades are and are not distributed.
Thank you, Roy.
Sure. So they've done that, and they found these big piles, putative big piles of hydrogen gas. Great. Normally, when you see these big reservoirs, big pile of hydrogen gas, some of that gas will have collapsed under gravity and made galaxies. So let's keep that in mind. The LATIS folks have found big piles of hydrogen gas that are usually accompanied by galaxies. Our team likes looking at galaxies. We like looking at galaxies that give off light from their stars, and we map the universe using galaxies. Completely complementary to the way the LATIS team does it. So we go and we look at galaxies and we try to estimate their distances based on redshifts, and then look where there are, this image is a funny image. Each dot corresponds to a galaxy. And you can see places where there are lots of galaxies close together and places where they're far apart. And we use a mapping technique called Voronoi-Monte Carlo. It doesn't really matter what it means, but it's a mathematical technique to map the distribution of galaxies and find where there are lots of galaxies close to each other in 3D space. And where those galaxies are close together, that's what we call a cluster of galaxies.
I'm not sure, actually.
Typically.
Roy, how close do they need to be before you call them a cluster? Call them a cluster?
Well, that is a very complicated question, because in the modern universe today, most clusters have the galaxies pretty well organized, and they've had a lot of time with gravity to build up. At the large distances that we're looking at, they're still forming. So if we go all the way back to this picture, you see that there's all these webs and filaments, and I can't zoom in right now, but if you were to try to find, if you look in this simulation, a well-formed cluster today looks much less well-formed in the past. Just imagine, think about Honolulu, what it looks like today, very centrally concentrated, tall buildings in one place. But if you go back a century, that's not there. The beginnings of it are there, but it's not as well defined. So, and we're looking back in time at these less well-defined things. We use computer simulations to sort of guide us to ways that we could observationally find these things.
Band image says there's not the same colors.
So we're looking at these galaxies, and sometimes we find lots of them together. And this is an example of a 3D map of one of these structures that are look back time of about 7 billion years. So we like to look at galaxies. That's easy to understand. We make maps of galaxies in 3D space, and when we find piles of them, we call that a cluster or a proto-cluster, which is a cluster in formation. Now, what's interesting is the LATIS folks and us happen to have mapped the same part of the sky in some cases. And there are a few cases where they see a lot of Lyman alpha shadowing. So it looks like there must be a lot of gas there. But when people are looking for galaxies, they don't see that many. So, but we expect that these big piles of gas should have made lots of galaxies. In most cases, what they see is a lot of hydrogen gas, a lot of galaxies. Less hydrogen gas, fewer galaxies. So they go together for most of them. But there are some weirdos where they do not. So that's a mystery, because in most models of the way the universe works, these shouldn't exist. So there are two possibilities out there. One is that there are some weird cases where galaxies don't form as efficiently in these piles of hydrogen gas. If that's true, and we've been counting galaxy clusters and how big they are as a means of sort of mapping the universe, but we're missing some because there are galaxy clusters that are only gas and haven't made lots of galaxies, we've miscounted. Or maybe the galaxies are there, but they're different than some of the other clusters where they're a little bit harder to find. So what we're doing here is we're going to places where they've seen a lot of hydrogen gas, but we don't see a lot of galaxies. Well, I should say that's most of the observations. One of the targets we were observing today has a lot of gas and a lot of galaxies, and we're observing that in the same way as the mystery ones, so that we can really understand how well those kind of systems compare. But in general, trying to discover whether these things are dark clusters or not.
So the target right now, Roy, is actually not the mystery. It's not the mystery target at all. This is a regular galaxy that actually has the gas around it that
It's a cluster, yeah. It's a cluster of galaxies that we see both the gas and the galaxies. So it's like, this is what normal ones should look like. But we're observing in a different way than other people have observed these before. So we want to use this one as a sort of control of, like, with the type of observations that we're taking, which I'm going to describe in a minute, what would it look like? This is what they should look like. This is what it looks like the way we're looking at it. Now let's look at the weirdos, and that way we have a sort of expectation of what a normal one should look like. So,
and by the way, I'll just point out this normal one that we're looking at tonight. This is probably one of the most massive structures ever found in the early universe. So it rivals Hyperion, which we've featured in other sessions. It's really hard to estimate the mass. You have to make a lot of assumptions about the matter distribution and how the what's called baryonic matter distribution. So the matter that you can see traces the baryonic plus dark matter, so the total amount of matter. But simulations are really helpful for this. We bake into our models a lot of uncertainty. So we have mass estimates, and then we have uncertainties on those mass estimates. but this structure is probably anywhere between 1,000,000 billion times the sun's mass and like 5,000,000 billion times the sun's mass.
1,000,000 billion on the low end
On the low
times
end.
the sun's mass.
On the low end, yeah. So we're pretty confident it's over 1,000,000 billion suns. And so these are some of the you know, we have the Coma cluster, which is nearby. This is about the same mass as that. That's not to say that this thing will evolve into something like the Coma cluster, but it's of the same ilk. It's the same type of structure. It has the same heft as the Coma cluster.
It's very hefty.
Yeah, very hefty. And so this is only, we're observing it when the universe was about 15% of its current age. So this is really, really the beginning stages of formation of these types of systems. So we're picking out the most massive ones because those are the easiest ones to find. It's really, really hard to find these things in general. And of course, you want to start with the tip of the iceberg. But as Roy mentioned, we're looking in some ways at the normal population of these really, really massive structures, and then the oddballs, and we're trying to contrast them and understand what makes one odd and what makes one normal. And that this is a whole new field, because these oddballs were only discovered through this amazing technique that our collaborators used.
Wow.
And as all good scientists, we have to accept the fact that it's also possible that our LATIS colleagues there's something amiss, something else that's confusing them.
How dare you.
Or there's something wrong with the people who've looked for galaxies before. But given that the way that the techniques work, it's hard to see what would cause like the kind of signal that we're getting. But you know, a lot of people think that scientists are like, okay, we know everything, and we don't. And like even before, Brian was talking about uncertainty. So it could be that there's something went wrong somewhere. Hopefully not. We've done a lot of checks, and looking for these galaxies is sort of one of those experimental checks to see why these things look weird. And then as you get more and more information, we get to have a physical explanation of why they're this way. Oh, this gas is hotter or cooler, so it cooled faster, or it's cooling slower and making galaxies slower or faster, or something else. You can come up with a bunch of different explanations of why these are weird, but you have to sort of collect the data and search out the avenues of what could have happened. And Brian's...
In fact, I'll just add to that, Roy. We're in fact, well, if one pathway occurs through these observations, if we find a certain thing, we're actually going to be proving ourselves wrong. So we're going to be proving that counting galaxies is not necessarily the best way to go about trying to find every single massive structure in the early universe, and that it actually takes an amalgam of techniques to properly constrain the number of these types of systems. And so we actually, I mean, not that we want to be wrong, but we kind of want to be wrong, because that's the fun part. And we get to see, like, we get to challenge our own assumptions. We get to challenge the assumptions of our colleagues, of our graduate students, of our undergraduate students. That's especially fun. That part's especially fun.
Well, a good way to think about that is to go back to this first diagram. This diagram actually shows dark matter. Right? So it's where dark matter, we don't know what it is, but that's what most of the gravitating stuff in the universe is. And the baryonic matter, as Brian said, which is the gas, the hydrogen, it's the stuff you and I are made out of, the carbon, the nitrogen, the oxygen, the iron, all that stuff, follows the gravity. It's the structure of the universe is driven by what the dark matter is doing, and its gravity is controlling it. But we didn't know about dark matter when galaxy clusters were first discovered. They were discovered as piles of galaxies. So we call them galaxy clusters, but in the early universe, it is possible that what are galaxy clusters today are just big, giant piles of hydrogen gas with very few galaxies in them in some cases. So in some ways, it's a semantic question. But if you want to know where the structure in the universe is, the underlying backbone of the material of the universe, maybe in the early days of the universe, galaxies are not the right way to go about making that map. So I think that's what Brian is saying. It's like, we're not really proving ourselves wrong. What we're showing is that the way that people have historically mapped the structure of the universe is not necessarily the be all and end all and be all for the early universe.
Yeah, and I'll just mention one other thing, addendum to that. One of our colleagues, who's the last person on that list that Roy was just showing, who's now a science operations specialist at Gemini, which is where I work, used our mapping technique a little bit closer, so about when the universe was half its current age, counted up the number of massive structures that we found in our data, and tried something very, very ambitious, which we had absolutely no idea whether it would work or not, to measure the total matter density in the entire universe, and this quantity called sigma 8, which is the smoothness of the universe on 8 megaparsec scales. So what is that? 24 million light years scale. Yeah. So very, very large scales. So the kind of like bumpiness, the variation of the matter field on these scales. And she was able to do it. And it was done for the first time ever with our data at these distances. And the underlying assumption, the results were predicated upon clusters are traced by galaxies. Everything that we did was galaxy density mapping. And so probably at those distances, it's a pretty reasonable assumption. Matter the universe is, 6 to 8 billion years old. It has some time to form its structures. And so probably that assumption is not too far off. However, when you start pushing back earlier and earlier in the universe, things have less and less time to equilibrate. And so you could get situations potentially where there's a lot of cool gas, a huge cool gas reservoir, but for whatever reason, whether that's the clumpiness of that gas or there's some energy injection from a couple of galaxies that cause galaxies around to not form, the gas is too hot, for example, it may not, this giant cloud may not form galaxies. And so this is what we're attempting to look at here. But if you were to just count out massive structures in the early universe and you were just to use galaxies as the tracer, specific types of galaxies or all galaxies, you may get the answer if you were to attempt this. If you were bold enough to attempt the same measurement, you may get the answer very wrong because you may be miscounting. You may have serious blind spots. And so even though you're saying, oh, well, I'm just, picking off the easiest structures to find, the most massive, you may be getting it really wrong. So we're challenging our blind spots this evening.
Wow.
Yeah, sometimes I talk about this in one way to think about it is imagine if you want to figure out where there is green stuff on the earth and the only thing you can see is trees. But then you're going to miss all the grasslands and savanna, whatever. But if you think trees should trace where there's greenery, then it's pretty good.
Right.
But there might be specific situations where trees don't develop, but there's lots of green. So we like looking at trees. The other folks are looking at the grass, and we're trying to see if they go together or not.
So I have a quick question about the clumpiness that you were talking about. If the hydrogen gas, if it's just hydrogen gas, how does it get clumpy? What are the clumps made of?
Yeah.
Gravity.
Yeah, gravity, basically. So it has
gravity.
It has like small scale, small level heterogeneities. So just you've seen the CMB, right?
Yes.
And so the cosmic microwave background, it's uniform to 1 part in 10 to the 5.
Okay.
So if you looked at, if you just looked at a map, not the traditional map of the CMB where you can see all the spots, but if you look at just the normal map, you take out the velocity field of the Earth and all these kind of things, it would look incredibly uniform. The start of the universe was incredibly uniform in terms of the matter field. But there's these heterogeneities that are 1 part in 10 to the 5. And all you need, like for erosion, It's just time, right? You just need pressure and time. And so you just need gravity and time. And eventually these small, very small level heterogeneities become larger and larger and larger and larger and begin to coalesce. And so I don't know, Roy, if you have like a good video of like any N-body simulation where like you see the initial matter field, it looks incredibly uniform, and then you watch the universe, it's in a simulation, so, but you watch the universe evolve over 13.7 billion years, you see like you wouldn't be able to pick it out at Z of 1100 where the last scattering surface was, so where the CMB is basically imprinted. You wouldn't be able to pick out oh yeah, a cluster is going to form there. But then you wait billion years, 2 billion years, 3 billion years, why not? You got time.
Yeah, patience.
And then all of a sudden, these start to straight out, these start to emerge and present themselves, and then matter collects matter, and then so things fall in on this filamentary structure, this cosmic web structure. The matter is funneled along these filaments into the nodes, which are the clusters. And so it's all fractal. So the universe is fractal in the sense that if you take a hydrogen gas field, it may look quite uniform, but it does have a center of mass. It does have some heterogeneity. And this, so gas then starts to coalesce, but as it coalesces, it starts to heat. But because it can interact with light, it cools through radiation. And this is where like a lot of the emission comes from. So hydrogen emission or oxygen emission, a lot of time, these are coolants. And so they allow the thermal energy to escape the gas.
I see. And so then earlier when Roy was showing us the energy levels, so my question there, I meant to ask earlier, but is that just ionization that he's talking about?
Well, that's just excitation. So it's slightly different than ionization. So yeah, so this is just jumping energy levels within the atom. Ionization is actually removing the electron from the atom and then completely, and then it can recombine later. And so like these are sometimes called recombination lines, because you'll see like when an electron is recaptured in the hydrogen atom, it'll cascade down and they'll start to make a bunch of different emission, including sometimes Lyman alpha. It's governed by these Einstein coefficients that are governed by quantum mechanics. But basically it cascades down to the ground state, emitting all these photons, and then it can get re-excited by these same photons. So Lyman alpha, a lot of times, it's what's called a resonant line, so it scatters all over the place, and so it actually lights up gas really well. So if you don't have very much dust, dust is basically
what is dust?
It's not hydrogen, not helium, and clumpy particulates.
It's another,
So dust grains is a complex molecules usually, and they can be excised by black holes in the center of the galaxies. So as gas is funneled into the center of a black hole, on the outer regions, the toroidal region, actually dust can form and it can be blown out into the outer parts of the galaxy. Same thing when a star explodes, it will create a lot of dust. And so this can destroy Lyman alpha emission very quickly. But if you just have like more or less pristine hydrogen gas, which there's a lot of it in the universe, a Lyman alpha photon will just keep scattering and it'll actually like light up the entire nebula.
Wow. Okay.
Sorry to hijack, Roy.
Sorry. Thank you for going back to that slide, Roy. That was so very helpful.
I think
We've circled Lyman alpha, but and these are downwards, so these are emission transitions. But if you just flip the direction of the arrow, then would be absorption, and this is the highest energy level up here. So if the electron were to, let's say it's down here at this energy level, or this one, if it absorbs a photon that has more energy than the jump from in here to out here, it gets ionized. So the electron goes bye-bye and flies off. So the electrons can absorb any energies higher than that and just go flying off. And there's some likelihoods of that happening. But that's what ionization is. So,
I think
and then
you're
when
right.
yeah.
Last six split, right?
Yes.
Yeah.
All right, so for tonight, what we're doing is we're using filters to try to find galaxies. So we're taking pictures and we're taking specific color pictures looking for galaxies. So you might see lots of pretty astronomical pictures like the multicolor one down here in the middle, but astronomers do not take pictures like that. We don't take pictures like your iPhone does. In fact, actually, your iPhone does what we're doing, but hides it all. What we do is we take pictures in different filters that let through specific ranges of wavelengths of light, and then we combine them. That is, in fact, what your iPhone does. All the pixels in your iPhone's detector either have a red, green, or blue filter in front of them. And then those are combined. So you have an R, a G, and a B right next to each other. And that is combined to make a specific color one, for that area of your image. It doesn't actually sense color. It has to make it up using filters. And that's what we do in our astronomical imaging. And the more filters we use, the more sort of information we have about what we think of as the color of a galaxy. So what are some of the filters we use in astronomy? Most of them are what we call broadband filters. So they span about 1,000 angstroms or 100 nanometers in width. So it's a range of wavelengths of light. We don't think of, humans think of colors, astronomers think of wavelengths. So B is like bluish, R here is reddish. So these over here are visible wavelengths of light, what we can see with our eyes. These are the colors of light that the sun primarily gives off in this sort of 4,000 to 8,000 angstrom, 400 to 800 nanometer range. We are observing in the infrared, which is what cats can see. Your body glows in the infrared. Warm things glow in the infrared. The Earth glows in the infrared. You're a little warmer than the Earth, which is why you're brighter in the infrared than the Earth. And the cops can see you with their drones and helicopters with infrared cameras. So usually we observe with these broadband filters because if an object is faint and far away, we want to get as much light as possible to be able to see it. So these filters are shown down here, and there's a bunch of different letter names for different filters. And on the top, I actually show what the Earth's atmosphere lets through. So there are in invisible light, most colors of light make it through the atmosphere. As we go to the infrared, you see these patches where light doesn't make it through our atmosphere. It's the water vapor and other things in Earth's atmosphere absorbs those colors of light. So it would make no sense to try to look through the Earth's atmosphere from the ground at these wavelengths. So you can actually see that these filters are matched sort of where the Earth's atmosphere lets light through. So we're observing in the infrared, which is like in this 20,000 angstroms or 2,000 nanometers, or astronomers love to change units all the time. So astronomers who observe at visible wavelengths use angstroms, which is 10 to the minus 10th meters. People who observe in the infrared, which is what we're doing now, use microns or micrometers. So we might say 20,000 angstroms or 2.2 microns, and we just switch these units all the time in our head. It's like switching between inches and feet on the fly, and it's irritating, but that's what we do. So typically we
Roy,
use,
you didn't talk about the godless radio astronomers that use
I'm not
frequency.
going to talk about Milajansky's first rating or whatever, so.
Good man, good man.
And then actually, well, radio astronomers talk in frequencies, not wavelengths, so they're crazy. So
Yeah.
so these are just some of the
frequencies. Come on.
we can leave that for question Q&A later. So now we're not looking at the hydrogen gas that's loosely out there. We're trying to find galaxies. Galaxies have gas in them as well, but they also have stars, and active galaxies have black holes and are making stars. And one of the things that happens in those galaxies is they can emit light at specific wavelengths due to processes happening in them. So we are looking at a different transition, not Lyman alpha, but hydrogen alpha, which is not going from here to here, from 1 to 2, but emission, so that electrons are going from the third n equals 3 level to the n equals 2 level. And that is a wavelength of light that is emitted in the visible if the galaxy was right next to us, if it had no redshift, at about 6,500 angstroms, which is a sort of reddish color. It corresponds to this line right here. It's drawn in red, okay? But because it's redshifted, it's out in the infrared. So what we're trying to do is, if we look at if we have a bunch of galaxies out in the universe and they're at different distances, different redshifts from us, and if they are emitting at this specific wavelength of light in the at rest, then that's going to be shifted to different wavelengths at different redshifts. So here we have example spectra of 3 galaxies. If you look carefully, it's the same spectrum, right? It has these bumps and wiggles. The pattern is the same, but they're shifted ever redder as they're ever further away from us. And if we were to take a broadband filter, as I've indicated with this green box, then they would, and we just look at how bright the galaxy is in that filter, they'd look pretty similar. This one might be a teeny bit brighter because it has this emission line in there, but in general, they look pretty much the same. But if instead we take a filter that covers a much smaller range of colors, smaller range of wavelengths, then if we do this, suddenly this galaxy at this specific distance from us, if it's giving off this specific emission line, will look very bright compared to ones that are not at this redshift or at this distance. So we already have broadband imaging of this portion of the sky. And now we're using a filter that happens to have been made, not for our purposes, but from someone else's science. They designed it a while ago. And it just so happens that the colors that it lets through match an emission line that would be for galaxies at the same redshift as one of these big piles of hydrogen gas. So that's the observations we're taking. We're looking for things that are going to be bright in this narrow filter, but faint in the broad filter. Galaxies at other redshifts will be faint in both, or very
Okay, so
in both.
Roy, you said that this filter was created for someone else's work. How do you make a filter? And is that something that you, as the science team, do you work with the engineers, at the observatory that you'll be using to make that filter, or do you have to bring it yourself?
Yes. So filters, there are companies that are optics companies. One famous one is SCHOTT, SCHOTT. There are many others. And what they do is they use different combinations of materials or coatings on pieces of glass that will let through certain wavelengths and not others. So an astronomer might say, okay, I want a filter that lets through these specific wavelengths of light, and they'll go to one of these companies and say, make a filter, figure out how to make this for me. And they'll put a bunch of coatings on glass that will block out certain colors, and that combination will let through only the colors that you want. And then we have standard filters, like earlier I showed these filter curves. Like these BVRI, GHK are pretty standard, but if you go from one company to another, when they make a filter, they're not always going to be exactly the same. So they'll actually measure how much light it lets through at different wavelengths. And you have to use that in your, data processing and measuring to really understand exactly what's happening. You get what's called a filter curve or a throughput curve. But yeah, you go to a manufacturer that's what they do. I mean, these kind of filters are not just used in astronomy, they're used in many other fields where you might need to isolate specific colors of light. Or in some cases, no one's ever made a filter like that before, and I don't know how to do it. Most astronomers or even astronomy engineers don't know how to do it, but these optics companies, they've been dealing with these various ways of making filters, and they'll figure it out for you.
I see. Okay, thank you, Roy. I was curious about that because I just assumed that the telescope would have all the filters that you needed already.
Yeah. So no, I mean, the filters go with a camera. So a telescope, Brian at the very beginning mentioned Subaru is an 8.2 meter telescope. So its mirror, its eyeball is 8 meters or about 25 feet across. It's a 25-foot eyeball. And what a telescope does is nothing else except be a giant eyeball. It doesn't do anything except collect light. And then to that telescope, you attach a camera, or we call them instruments, that does something with that light. Maybe it takes a picture. Maybe it breaks it up into its multiple colors and makes a spectrum. Maybe it does something else, or it does multiple things. And in that instrument is where you insert, in that camera is where you insert the filters. So in a way, you can think about it as like if you use a DSLR or a SLR camera, you have the lens, that's the light collecting thing. But then you have to attach a body that does something. So in this case, we've asked that they insert this specific filter. And I don't remember exactly how many different filters, like 5 or 6, this instrument can hold at a time. But a different observing team may want different filters, and then the engineers at the telescope, the telescope staff, will swap those out during the daytime so that you have the ones that you need.
I see.
Yeah, one of the really special things about this instrument, it's actually both a spectrograph and an imager. We normally use it as an imager, but it's equipped. Subaru is wonderful with this. They have so many custom filters, and it's in part because the Japanese community is very interested in providing custom filters for the observatories. They work in tandem with the scientists, primarily in Japan, teams in Japan, to help fabricate filters. MOIRCS has 3 filter wheels. So a lot of other instruments have 1 filter wheel or 2 filter wheels. That's 3 filter wheels, which means that it's a big rotating, it's basically just a circle that's driven by a bearing, a motor. And these 3 filter wheels each contain probably somewhere around 6 to 8.
Wow.
Kentaro, how many filter wheels total does MOIRCS have?
8.
Or sorry,
Eight
slots.
8 holes. So you can input 7 filters and 1 vacant hole.
So 20.
So 7 filters for each field.
So 21 filters total. Yeah.
But some filter holes for cold stop, so it can for some specific part for infrared instrument. Because infrared instruments usually don't have shutter.
Right.
Very interesting camera.
Yeah. So it's basically a
Yeah, but there are more than dozen filters.
Yeah, it's called a cold stop. It basically just stops the thermal emission from coming in.
Oh,
that's the technical name.
It's some, how to say, it's like a buffer for summer radiation.
Right. Yeah, except for summer radiation.
Yeah.
So it's basically like an ice cube above you, but it doesn't melt.
Sky is very bright. Yeah, it doesn't. Night sky is very bright, too bright. So
yeah.
So you need some like a sunglass or visor for instruments.
But yeah, so that probably in total there's near 20 filters on Subaru and a lot on MOIRCS, and a decent number of them are medium band and narrow band. So for custom purposes.
incredible. And is this what we're looking at now? Is this the instrument panel?
This is a picture of MOIRCS mounted on the backside of the telescope. So these things are complicated. Infrared cameras need to be.
Doesn't look that complicated, right?
Yeah. These astronomical cameras are not off the shelf. Everyone is custom and distinct, handmade. In near infrared instruments need to be kept very cold. Even visible light instruments, we keep the chips, the detectors in liquid nitrogen, but infrared ones, because infrared light has much less energy, any heat will show up as light in the camera, so you have to keep it close to a few degrees above absolute zero. We're talking about liquid hydrogen cooling. And this instrument, it's probably 6 or 8 feet tall. So these are big cameras. And just for scale, here's a different instrument that goes on the same telescope called Suprime Cam, and you can see a human being standing next to it. And there are other instruments that are the size of like a shipping container and are mounted off to the side of the telescope because you can't even attach it to the telescope. You have to send the light into the instrument on the side. So, yeah, these cameras are very impressive technological achievements. And
Incredible.
so it doesn't look anything like a camera that you're used to seeing.
No, it does not. It looks like part of a spacecraft.
Exactly, yeah. So this blue area up here, the top is the back side of the telescope mirror. So the light comes in from the sky, hits the mirror, goes up, hits another mirror, and then is reflected back down through a hole in the back of a hole in the middle of the telescope mirror and into the back. It's called Cassegrain focus. Subaru also has the ability to, unlike most large telescopes, to put a camera at the front of the telescope so the light comes in from the sky, hits the mirror, and goes straight up into the primary focus, which is what where this other instrument lives. But yeah,
And Taro, not to put you on the spot, but do you know like roughly how much the prime focus spectrograph weighs?
How much what? I cannot understand. How much?
PFS? Do you know how?
Wait. I don't care about that.
I feel it's got to be like 5 to 10 tons, something like that. Does that sound right?
I said 5 tons is too much.
Too much?
Too much
Okay.
hotel. Yeah, I like it 2 tons like that.
2 tons. Okay.
Yeah, 2 tons. Yeah. Yeah, almost all, except for Nasmith instruments, it's limited by like a 2 tons scale.
Yeah. But a lot of the weight of the instrument is offloaded to the Nasmith deck. Is that right or no? For the prime focus spectrograph?
And in fact, spectrograph itself is not located on the top of the telescope.
Right. Yeah.
It's only fiber module and optical correctors, many big lenses. So yeah, lenses are shared with HHC, hyperspectral cam, and PFS. Both instruments share the same optics.
Okay. Okay.
Yeah, that's a kind of a trick, or how to say?
Yeah. No, that's
Yeah,
great.
it's a difficulty to install both instruments. Yeah, so such big lenses covered wide field of view and very sharp. It's kind of a technological breakthrough.
Yep.
Yeah.
Yeah. Totally.
Yeah, of course, some researchers want to hyper wide field infrared imager.
Yes. Yep. That's coming.
But glass material is different from optical instrument and infrared instruments. So it's very difficult to make big lenses for infrared instruments. And so our future instruments give up the size of field of view, and now they shrink the field of view.
Oh, I didn't hear this. This is for ultimate.
For category instruments, it's a category instrument, but
Okay.
even in category instruments, it's very difficult to make a big lens.
Yes. I
And
know. Working at Gemini, I know.
yeah, and not it's decided by physics, so not all telescopes share the same problem.
Yep.
Yeah, so I put up a diagram of the Subaru telescope here. So over here is what we call the main mirror. So light comes in from up high, from the sky, through the dome, through the open slit on the dome, and hits this primary mirror, the main mirror, which we call the primary mirror, and it sends light up towards near where it says PFI or cable C. That's what's called prime focus. That's the first place where light comes to a focus. So the instrument we're using today is not up here, but the one that they were talking about called PFS, which is a brand new instrument that actually our team was one of the first ones to, I think we were the first ones to do like regular science with it.
We were the
Back in
first
March. Is a spectrograph, so it takes spectra, makes rainbows of light, It has optical fibers that that a little robot basically moves around. It has 2,400 fibers, so you can take spectra of 2,400 things at once.
At one time.
At one time in a field of view that is bigger than twice the full moon across. It's a very wide field of view. So Subaru as a big telescope is one of the only ones in the world, maybe the only one, that has this capability of being a big 25-foot class, so an 8-meter class telescope that has such a big field of view and can put these heavy instruments at prime focus. There's this big metal ring at the top and a big heavy structure, which like Keck does not have. So that telescope, the little robot and the fibers are up here, but then the light is fed through those optical fibers into the actual things that make the rainbows and record them. Those are so big that they have to be offset to the side of the telescope, and they're fed with fiber optics.
About how big are they, Roy?
I don't know, but
Not sure.
maybe Brian knows how big the photographs are or so.
Kentaro, do you have like an idea of the size of the 4 spectrographs for PFS?
Spectrograph size. Spectrograph size is kind of your half of your control room, your room. Yeah.
Is 1 spectrograph.
No. 4 spectrographs.
4 spectrographs.
Yeah.
Okay. Okay.
PFS has 4 spectrographs. 4 spectrographs.
Okay, so roughly, let's say it's 3 meters by 4 meters by 3 meters.
Yeah, it's very huge. Yeah, huge.
Yeah.
The size of a small car. Each one is the size of a car.
Size car, camper van.
Yeah. I don't know, a US small car, Roy. Let's
Yeah.
Wow.
Not a smart car, but like a Nissan Leaf, or even bigger. Anyway, they're big.
Huge, yes. Wow.
But the instrument that
huge. So huge. So it takes a while to cooling down, and also it takes a while. I don't remember how much time, but not quickly to warm up and or cooling down immediately. So it takes time.
Right.
So if something happened, we have to wait for warming up for cooling down.
it's like stopping a moving train.
Yeah, if something happens, it's very annoying.
I bet. Thank you, Kentaro.
But the instrument that we're using.
Maunakea Summit is very good condition for astronomy, but not good condition for electricity or power line. So more often happens power outage. Sometimes very heavy.
Imagine. Wow.
Yeah, we don't like it when power goes out. That's not fun. And we all work together as a community. It's sometimes actually there's certain lines that feed to Subaru that don't feed to Gemini, some that feed to Keck that don't feed to either of us, or some that feed to all of us. And so a lot of times if power goes out at nighttime, all the operators will work together to try to diagnose the issue. We'll work with the Hawaiian Electric Company to try to, they'll get people out usually pretty quickly, because these instruments, if they have what we call uncontrolled thermal cycles.
That sounds bad.
That sounds as bad as it is. It's almost equally bad for optical instruments as it is for near-infrared instruments. And each instrument has its own peculiarities. So we've actually had like bacterial growth in one of our instruments because of a uncontrolled thermal cycle. Yeah, Maroon X had bacterial growth in it. Yeah.
And these are not, I mean, you saw the sizes of these cameras. They're incredibly expensive to build because they're all custom. So you're talking about a few $1 million for the cheapest ones, and the most expensive ones are on the order of $50 million to build.
Yep.
So you do not want to break it. And the time is very valuable and very precious on these observatories. So, there are other instruments, but like we can only do our science with MOIRCS, and other people can only do their science with PFS. So if the instrument breaks, that messes up all of the scheduling and messes up people's science. So it becomes you really don't want to cause trouble.
That's right.
I
I
don't know,
promise to be good this time, Roy. I won't do anything.
I'll give you a little anecdote about breaking instruments in a minute.
Okay.
But yeah, so we were talking about PFS, but MOIRCS actually lives back here behind the mirror near where this like little black disc is. And that's called Cassegrain focus, named after a French optician, astronomer who created this design. In that case, the light hits this primary mirror, goes up here, and you put a mirror here. And that reflects the light back down through this hole, this puka in the middle of the mirror. And then you can put an instrument back there so it's not in your way, and you can attach something pretty heavy to the back end of the telescope because you have this big, massive mirror there. So it's called the Cassegrain focus. You might also notice in this diagram that there's like a hole in the side here where the telescope is attached. So you can hit the main mirror, hit this second mirror, then put a third mirror in the way here and send the light out the side to a camera that lives right there.
Wow.
So it's called Naismith focus. So there's many configurations that can exist depending on the size of the camera and what you need.
Just swap channel 1 and then swap channel 2.
I mean, things do happen with telescopes and instruments. We had a night once with, I think it was, maybe Brian will remember, was it SuprimeCam where we had the glycol leak?
No, it was Demos.
No, we had it here at Subaru. There was some kind of coolant leak. Yeah, it was one of the
I don't think so. It might have been MOIRCS.
I can't remember. But yeah, something happened. One of the hoses that carries coolant, something failed, and it just started leaking its coolant all over the camera and the telescope.
Oh no!
Yep, that stuff happens. In the early days, I was observing at Keck, and that was when you had to go to the summit to observe. And all of our observations were going smoothly, and all of a sudden, all the alarms in the observing room started going off, and the whole telescope came to a crashing halt because the letter Q key on the keyboard had gotten stuck in the down position. Had sent a million letter Qs to the control system and crashed it.
Oh no!
So one broken keyboard.
A stuck key did all of that.
Key did that.
Wow.
And my second observing or never when I was an undergrad student, so a long time ago, I was actually using a multi-object spectrograph, one of the first ones on a telescope in Chile. My professor advisor had let me design the observing program, and we went there, and that one used robotic fiber.
Yeah.
So background increase.
Yeah. It's the clouds.
Not the instrument.
Yeah, that was my supposition. Vin and I were just talking about it. So yeah, good. Okay, well, not good either way, but better than the instrument, I would say.
Oh, I said it's black.
Yeah. So
what just happened, Brian?
So we there's some thin clouds coming in, and at these wavelengths, it kind of acts as a scattering device. So we just saw a jump. We're actually monitoring on this. I have to sign into Zoom for every single one of these screens. So we did this in the past, but screen right here, we're monitoring the data as it comes out, and we're monitoring the average number of counts that we're getting. So how bright it is basically as a function of time, and not like any, astronomical object, but just the sky. How bright is it? And we just saw a big jump in the sky brightness. And there was a little bit of a worry that was last night we saw a little bit of extra light in the instrument that could have come from some thermal radiation inside of the instrument or some scattered light. But tonight it looks like that the staff did an awesome job of fixing that. And so this is actually coming from clouds.
Okay.
But
Some clouds are bright in infrared. Yeah, usually clouds block the optical light, so more dark. But some clouds are bright in infrared, so infrared lights increasing. Yeah, so infrared light world is very different from our normal world. So some strange things happened.
That's true. Very strange.
Yeah, and we're full moon basically tonight. It was last night, but yeah, we're full moon basically tonight. So moon's like not like directly overhead, but it's getting there. And so yeah, it's backlit on top of backlit on top of backlit, and so we're getting the wrong type of backlighting right now. But it shouldn't have too much of an effect on our data. We just saw it jump back down, and basically what this does is increases the background by maybe 20%. And so this will add like maybe 10% more noise to our data. So it just makes it a little bit harder for us to get a deeper exposure. But especially if they're moving fast, they could pass away. And we're taking, 2.5 hours of exposures on these fields. And so if we have a couple of frames, 3-minute frames where clouds come in and mess with the background a little bit, we clip out those data. So we were cognizant of that. In fact, I'm guessing Finn took a note, like the last frame might have had some higher background, and then when we're doing the reduction of the data, the processing of the data, we would say, okay, let's throw that out. Or there's some automated routines that will identify high background, and it'll automatically clip those frames out from being included with the better quality frames.
I see. I did notice, in fact, that just as that second, we got the second spike there, which it is lower. I saw Finn start input data there in the chart. So I was actually going to ask you, is this what you were recording? But what are you recording? And I assume you and Joel have maybe similar but slightly different responsibilities on the team tonight.
Yeah, so I've got a spreadsheet here that I'm recording a few different things. And so there's a record kept of each exposure that's taken by the telescope, whether it's taking science data for what we're looking at, maybe it's getting something called a dome flat, or looking at focusing the telescope, those sorts of things. And so just as a second log, instead of what the observatory has, we keep our own log. We're essentially writing down, okay, this is the target we're looking at for this portion of time. This is the filter we're using. These are the frames of data that are being taken. So later, if we're doing the co-adding, like Brian was talking about, we can record, okay, we know that these frames might have this issue, and we can, clip those out, not use those. I also take different notes. Every once in a while, we'll check the seeing. So we'll see how much distortion the atmosphere is causing with our images. And so sometimes you can see the seeing kind of vary throughout the night, where there'll be less distortions, there'll be less things happening with the atmosphere, and we'll get clearer pictures. And you can kind of see how, and that sometimes affects your data quality that you're putting in. So kind of taking notes of that as well. So just kind of keeping a running log of everything that's going on. So later, whenever we sit down and actually try to reduce the data, do something with it, we have some memory. And it's especially helpful because we're only on first half tonight, so we're done about midnight here Hawaii time. But sometimes you start, at 7 p.m. You go all the way till 6, 7 in the morning, and trying to remember what you did like a week ago while you were half sleep deprived. It's nice to write something down.
Yeah.
So that's always a good habit to have, just to have some things. And I've definitely taken notes during these sessions where I go back and look at it. I'm not really sure what I meant, but you're able to piece together what was going on.
Right, exactly. What you were hopefully trying to convey.
Yeah.
That's right.
So try to keep it very clear and try not to add too much to it, but easier said than done, depending on time of night and other things going on. So.
I can imagine, Finn. Yes. So, Roy, how do you all assign responsibilities on the team? Because you have like Joel as an undergrad student, and then Finn as a graduate student, and everyone is learning and growing and adding to their skill set. How do you all, as the senior members of the team, help your junior members start to step up?
By leaving them to do the work. I mean, it's in a way like
that's the answer. That's it.
I mean, really. Actually, well, I think of it as an apprenticeship program, just like in any trade. I mean, yes, our field, right? We have physics, knowledge, math, and things like that. But designing an observing program and planning a proposal takes work and experience. And so you look at previous proposals, they join as like co-investigators on proposals where you write, but they see it and comment. And then it comes time for them to write a proposal and they need some hand holding and some advice. And then they're ready to do it on their own and maybe come and ask you when they have questions. And it's the same with observing. This is not Finn's first rodeo with MOIRCS. It is Joel's. But so
In
you
person.
start
In person, yeah.
In person,
in
yeah.
person. So, we talk about, we have weekly group meetings where most people are present. So we might talk about stuff. There might be subgroup meetings about observing planning. We do a lot of communication by email. And at this observatory, you create an observing file, which Brian did in this case, where you list all the commands that they're going to execute, that the staff at the observatory will execute for you. And then the junior members can see what's in that file and use it as a model for future ones and ask why you're doing things a certain way. And then we let them start. They watch you drive for a few hours or something, and then you say, okay, now you start doing it while you're watching over their shoulders. And then the next day they start taking the lead. And when they have
You take a nap.
yeah, then you take a nap. When they haven't broken the telescope and the data is okay, then it's good to go.
I love it. It's wonderful.
0.44.
Yeah. So,
I'll just mention really quickly that in Finn's case, so the first time we ever observed on the prime focus spectrograph, so this is the first ever classical night, so the first time basically it's been used for science. This was done with a program from a professor PI, principal investigator at UH, Dave Sanders. And so this was him proposing,
Yep.
and then he joined with us to work through the observing plan, and then for some of the observations, Finn and I were physically in the room taking the observations,
Just
but
down the hall around the corner.
but Dave was behind the scenes helping to prepare everything. And now Finn has proposed and proposed successfully as a principal investigator himself. So he's now partially graduated, not graduated all the way.
Yeah. Well, I mean, I'll take it if
Don't
you
get cocky.
I got a little ways to go, I think.
But so in January, mid-January?
11th, 12th, 13th.
11, 12, okay. It will be Finn's first nights as a principal investigator on Subaru of any instrument, right?
Yeah.
And you picked a heck of an instrument for your first instrument.
I'm excited. It's good. Hopefully weather's as beautiful as we're getting tonight, and that's for the most part. So.
Yeah. So yeah, that's a session. We're gonna do hopefully a shadow session, and we're hopefully gonna be doing it. We're gonna be doing, unlike tonight, we'll be observing from the summit, because one of the part of what part of the training for younger astronomers is to actually physically be at the telescope. We lose it. I mean, it's amazing to be here. I'm 3 minutes from home. I can go home, get a sandwich, come back. It's nice and air conditioning. We have our full oxygen intake, so we're again happy astronomers, breathing comfortably. And it's not cold. We go after the night's over. We can go down to the beach in 2 seconds and take a swim. But we lose actually physically being at the telescope, and there's certainly grandeur that imposes itself on Maunakea, or indeed anywhere that you observe from a mountaintop. And there's tons of things that you can learn by physically being at the telescope that you simply, your imagination has to do a lot of work down here. And so you don't really have an understanding of the scale of these things. We can talk about refrigerator size or, camper van size, but that to see it, and then not only to have that visceral, you all right?
Yeah.
Okay.
There's something, yeah.
Okay. That visceral connection to the instrument, to the size of the telescope, to the Mauna, but also to see the inner workings of the telescope, to see, okay, so that the light goes there and it bounces out there, and then it enters in here, and what is all this cabling for, and how does this, and then if we move the filter wheel one, like where is that mechanism? Where is it in the optical path? It was I was at Gemini for 2.5 years before I actually entered the dome of Gemini. And that was because of COVID and my son was born. And so I didn't have an opportunity to do that until 2.5 years afterwards. And it was hard. It was hard to envision. I was in charge of some of the instruments. It was hard to envision what those instruments looked like, even if I had optical diagrams and I had, tons of experience from here at Hilo. And so this is one of the wonderful things that Subaru allows. They allow PIs that are graduate students, principal investigators that are graduate students, to go to the summit. And then I say, can I come too? And they say, no. Hopefully they say yes.
A babysitter. maybe.
Who's babysitting who?
Yeah, well, depends on,
Speaking of taking
oxygen levels and other things, yeah.
Well,
I
that's,
think-
that's congratulations.
you,
That's
thank you.
incredibly wonderful. Wow.
Excited for that.
And I think taking that kind of ownership and that leadership and also even accepting risk. I mean, in science, we have projects that don't work, instruments that break, and things like that. And that's just part and parcel of the way we do things. So, but you feel ownership of it and responsibility, so that makes you want to do better. But it also, you can accept those trips. Sometimes those stumbles. I was gonna say, when I was an undergrad, my undergraduate research advisor, he was observing stars near the center of the Milky Way, and using a multi-fiber spectrograph, which at that time was high tech, had 24 fibers, not 2,000, but 24. And they were on little robotic. The way that
24 is a lot. I mean, I was doing single slit spectroscopy in the near infrared for a long time. And that was on Keck. That was near spec on Keck. And that was in my grad school. That was only, well, I won't say, but that was only 15 years ago. And so it was single.
Have infrared detector, so it's an infrared detector for very expensive for non-US countries. So
Yeah, so this instrument was called Argus on the 4-meter at Cerro Tololo. And the way it worked was it had a metal ring with these rods basically that could pivot and move in and out in length with optical fibers on them, 24 of them. And we had computer software, and this is relevant for us talking about young astronomers, that you could design where those fibers would go. And my advisor, who was he's a little younger than I am now, but he wasn't interested in learning that software. Like, he knew how to do his thing, and he was senior and he didn't want to learn. So the young people, that was me. I was an undergraduate student, a junior in college. He was like, you go design the observing program. He handed me the target list, and I had to figure out how to run the software.
Wow.
And it was supposed to figure out, like, you could move these little robot arms in it, and it was supposed to have checks to ensure that they didn't smash into each other. So you can already see where this is going. We go to the telescope, and we deploy the first setup, and it's fine. And we go to the second setup, and what happens? The robot arms collide and are trying to go where they're supposed to go, and promptly break off the ring in the middle of the night. So, and I'm an undergrad student, and I'm like, I just broke this high-tech instrument.
Oh, that sounds disastrous.
That sounds disastrous. I mean, we lost half the night, and the technicians came and fixed it. But I mean, I'd used the software. It turned out I didn't make the mistake. The software didn't have the correct collision avoidance in it. Right. But I mean, I was scared out of my mind. I was an undergrad, and at that time, undergrads didn't go observe very much. It wasn't like today. I was even told by my advisor, like, pretend you're a grad student. So when people ask me, what year are you? I'm a third year. But that stuff happens. I mean, we have had instrument failures. We've had masks that were designed wrong. And that's part of the learning process is, oh, I made this mistake, I'm not going to make it again. Or I learned something new about the software or the design process or something else. And, when you release these youth into the wild to go do their own programs, that's just part of growing up into being a fully professional astronomer.
Right, that's right. And part of, I mean, this is part of our goal here with Shadow the Scientist is to be able to show that and to talk about that. And so I appreciate having Joel, Finn, and of course you and Brian here as well too. But to see that graduation, how the skill levels, how you get that, and of course making sure that we share with everyone that yes, science is a process, and there are going to be mistakes, and that is okay. In fact, it's needed, and it is to be accepted if you're going to be in this field. And I know that can be a huge problem for some people. And to really hear you scientists sharing with us your kind of horror stories, and yet you lived through it and learned and are still doing amazing things, you can get past it. You learn from it. And I appreciate you sharing that, because so many people need to know it. They need to hear it.
Persistence. Oh, go ahead.
No, please go ahead.
I mean, I've been on an admissions committee for the graduate program at IFA before. And I think the number one thing probably we look for is people to demonstrate persistence, because whether it's having to write proposals for your telescope time and being told no, or asking for money and being told no, or doing your observing and you're clouded out, or the idea that you had doesn't work out, being able to persist and be creative in how you solve problems that you come across, and in coming up with new ideas. That's like the hallmark of a scientist. It's not like being the best mathematician or having the best physical intuition. A lot of the basic things that you need are like persistence and creativity. And so those are the things that we want students to develop.
Brian, switch to SWCF.
You got it.
Right?
Yep.
Yeah. Okay.
You have to unwrap or move around.
Yeah, no problem.
Yeah. Okay, so yeah, we're just moving fields now. We're actually flipping the instrument 180 degrees. So yeah, we're in the same part of the sky, but we're just rotating around we have different systematics in different parts of the instrument. So different properties of there's 2 detectors on MOIRCS. And so each one of the detector has different properties. And so we're kind of averaging it out over the entire exposure. So we do about half of our exposures at one angle on the sky, and then flip around 180 degrees and do the other half like that. So just flipping around.
So making use of both of those detectors.
Exactly, yeah. So both detectors are in use for both rotation angles. But one has, like, for example, last night, there was additional light in detector 2, but not in detector 1. And so we wanted to mitigate that issue by sharing the love on both sides.
I see. So the telescope, your things are being moved right now, and then once you're settled back on the target, would it be possible to see maybe a raw image?
Yeah, absolutely.
Yes, we can.
Yeah, totally. Yes. I just want to add to something that Roy said, which is that it certainly is not limited to third-year undergraduates or graduate students, or even young professional astronomers. I mean, when we become a professional astronomer, it's not that we're less wrong. We're usually still wrong about 95% of the time, and we're still told no a decent fraction of the time as well. But we ask more complex questions, and the point is persistence. So, I mean, for example, I spent all day calibrating an instrument on Friday for Gemini. We got to nighttime, and I was like, yes, we're ready to go. And I wasn't actually observing. I was home, like, trying to enjoy dinner with my family. And I get a call from the control room, and something's wrong. And we spent an hour and a half on the phone, trying to diagnose the issue. And there was, 3 highly trained people on the call, and then myself. And we couldn't figure it out, but I had a kind of hint of something, and I said, let's move on, but let's attempt something in the morning when the sky is a little bit brighter, so we're not using like really high leverage telescope time. And so, yeah, please. And so I put in a test sequence, said, yeah, move on, you can do other observations, because the Gemini, we have a lot of different instruments, so we just kind of switch between things. And it turned out in the morning, that was the issue. We diagnosed it and it was correct, and so then we were able to go on to observe the following night. But it's very complicated. That particular instrument has about 27 different modes. They all have to work together in tandem. And so if one thing gets off kilter, it can be very difficult to diagnose. And so this is daily life at an observatory. I mean, even the scattered light thing that happened, it wasn't like it kind of came out of nowhere. There was hints of it in the observations the night prior to us being on. There was some attempts to mitigate it last night, but it looked like it somehow it kept going. And then tried again today during the excellent staff here at Subaru attempted another fix, and it seems like for the most part they've been able to find a way around it. But these instruments are incredibly complex, and the way that they interact with the telescope is incredibly complex. And the way that all of that interacts with the environment is incredibly complex. And so we have, 100 staff across our two sites at Gemini, all trying to figure out how these behemoths work.
Yeah.
And we get it wrong a lot of the time, but we keep testing, we keep pushing, we keep trying different things. And in the end, sometimes we get it right.
A lot of times they get it right, a lot of times. But that is key, persistence.
I was looking at this, right? Yeah. This is the last. So that's.
It should be a reason.
That's okay, that's what I thought.
But you're probably, so we just flipped, right? So we have to wait until we have the.
Well, I was doing the last dithers of the non-flips.
Oh, I don't know if you took a couple of other.
I thought that's what it was from.
Just started for.
No,
Oh, that's what this was from. It was from the last dithers, the 8.6, 8.4, and 8.3.
Well, we have a lot of frames up here too. This is definitely a reduced image. This is the actual. It looks like I would wait.
Okay. Then we set.
Yeah. Yeah, because I think we just have 180 seconds until the next frame comes out, and those two should be. The other thing is that
Yeah, we've been getting.
sky is has a lot of variation right now, and so when you subtract off the last two frames, you may be having a bias level between the two, and so that may be what we're seeing there.
Yeah. If the pixel value did not make sense, it's as well.
Oh yeah, okay, yeah. Well, let's see what comes out in this next experiment.
It was a 0.5. That was before multiplying it. So
How do you mean?
I mean the pixel value in the bottom middle was 0.5. So like not with this, but with the original. Going here. I did
Again, that's probably a snack. Because these values are like 2,500 pounds, so it looks like we just had a big jump in the sky brightness between the last two frames. So yeah, let's just hold off. We'll try to reduce the next two frames and see.
Okay. Then after
Because you see like the counts on that are 2,500, and so you see these jumps. These jumps are roughly 1,000, or I mean some of them are
at least
14,000 to 10,000, so 4,000 counts.
yeah,
So if you're subtracting off two frames that are 4,000 counts, it would be another.
one's gonna look significantly better.
While we're waiting, you guys, like Joel, do you want to talk about the science that you're?
Yeah, let me just share my screen real quick.
Yes,
Sorry.
please.
Yeah, in the end, Joel is doing a lot of the data like the data analysis, and he's actually selecting the galaxies out. So he's currently writing a paper on well, what are these things, and do they have the properties that we expect, or do they not?
Well, that's exciting.
So I'm sure this is, can y'all see?
Yes,
Yep.
yes, we can. Yes, Joel, tell us about this.
Okay, so,
Do you want to move over here?
Yes, please.
yeah. Where would be?
Right here.
Anywhere is fine. Yeah.
Okay.
All right, so I know that,
Feel free to sit down. The camera's always.
so as Roy talked about and Brian talked about before about why we chose narrowband broadband images. I'm using a broadband called the J-band and a narrowband that follows, I believe it's relatively close to the center of that J-band.
Pretty close, yeah. I think it's 1292. Is that right?
Yes,
Yeah.
that's what I
Yeah, a little bit on the red side of the event, but yeah.
So right now, what you're seeing is the J-band image. This is just kind of, I smoothed it a little bit, so it looks a little bit nicer than it normally does. What I did is
And so just for context, this image here was not taken by Subaru, it was not taken by
no,
us,
this
right?
was taken by Vista.
Vista, yeah, so this is a
Chile.
instrument in Chile, yeah.
Yeah.
Telescope instrument in Chile. And so this is a 44-meter class telescope, and they just stared at this part of the sky for a very, very long time. This is really one of the deepest images ever from the ground in this band.
And I did the same for, I believe, the H and KS bands as well.
Yeah, why JHK, and they actually had a narrow band, they were looking for Lyman alpha as well. I forget which like that's but yeah, in the Y band, J band, something like that.
Which is very nice, and then we was able to she was able to combine the all three images, the JHK over this region. Sorry, I'm trying to figure out where to look. Yeah.
Anywhere is fine. People can see you like 5 times.
This is true.
Our collaborator, Lu Shen, she is a postdoc at Texas A&M, I think.
And a new mom.
That's true. That's to her, yeah. She has helped a lot with the data reduction. She helped, her and Brian, actually taught me the whole process. And so I've just been, I guess, creating a lot of code for myself and trying to run the data through myself to make sure that we get these emitters. These emitters are selected through a series of cuts that are done. So there's typically a lot of noise in the image that we're trying to make sure that some of these stars aren't, or some of these galaxies aren't. So our goal is to try and find a way where we can determine that if those galaxies were not just noise. That was one of the main cuts. Another one was, I'm trying to think, there was like that was the 5 sigma line. Then there was color axis. My mind's blanking on how to say that in a different way.
Yeah, it was just a change in color. So like, yeah, so the significance of the change in color. So it just like Roy showed these different images with these different, like a galaxy would look different in different bands. And so you go all the way from the blue to the red to the infrared. And so that's what we call color as a astronomer. And so color excess is another like a fancy astronomer term to say basically like it looks red. Or blue. Or blue. Yeah. It's usually red because of the way it's like yeah, it would be negative if it was blue, right? So it would be a color decrement. We want to sound really fancy. So blue is color decrement.
That is fancy. That is super fancy.
Sound very self-important. So yeah, and then there's also the depth of the image, right? So like how deep you take the image, and so there's only certain brightness things that you can see, And that, depends on how long you're imaging for. It depends on the size of your eye. 8 meters, 4 meters, 2 meters, 30 meters. And so that matters a lot. And so those are the cuts I think that you made. Right?
Yes, those are the main cuts.
But so you combine this image with another image, right?
The J-band or the,
Well, so in order to make these like the color excess, you're looking for stuff in this like narrowband
Yes.
1292, right?
I was going to discuss just like the visual inspection parts, just because the code may tell us one thing, but yeah, it's not gonna look for artifacts within an image. An artifact is just any extraneous things that happen during an observation run. Like if you see right here, there's this kind of large, like long wet line right here that goes from this, you see my mouse, this massive source. So this, it doesn't necessarily detect any, it can like list a source on here that we might not trust as much.
So just for context, this image here is now no longer from Vista. This is from Subaru, and it's from an instrument called SWIMS, which is no longer on Subaru, but sort of a very similar function to MOIRCS, is now on TAO, another telescope. And so this is a narrowband image of the sky, very similar to what we're taking tonight. Yeah.
And how I visually inspected these emitters, at least. Are you doing the checking for that?
Oh, I got it. Yeah. Sorry, my computer's about that.
So how I visually inspect it is typically you look around the area relative to the broadband image, the broadband being the Vista image. And you try and see, or the goal is to see how much of that remnant flux or light that is remaining in the narrowband image. So if it shows out significantly more or appears to show up more, then we can determine that it's more viable to be, or it's more likely to be a genuine emitter. So I would say that this would be a decent example. I mean, yes, it's by a giant source, but that giant source is a lot less bright in that narrowband image. A poor example would be where my mouse is right now. We typically, it'd be easier to see when the color of this is inverted.
Oh, that makes a big difference.
Yes, it does.
Wow. Oh, yeah.
See?
You can clearly see
You
that.
can clearly see it, as opposed to where it's just normal color, where it's just a bunch of light that, I mean, I don't know about you, but I can barely see that, right?
Yes, absolutely, that's it.
So you see this, the source I'm showing right here, it's, I mean, if you see the size of this massive source or massive star, it's hovering most of the screen right now. So when you flip back or blink between the two images, it's just flipping back and forth.
I can't see anything.
There's this smaller emitter that is
3,000 pounds.
Yeah.
Traction.
So
Can you do that again, that
yes,
blink?
I can.
The blink comparator,
Yeah.
I used to do that. Yeah, okay. Huh. There it is. Yes, okay.
And I can go to, actually, we found the majority of our sources in the lower part of the image. Some are closer to each other than others, but the ones right here. Look at that. And the broadband image, it's up. There we go. It looks very minimal, right? It's not that much. Flip to the airband. Look at how that changes. I mean,
Wow.
yes, the aperture is a little bit off center, but or the actual selection's a little bit off center, which I've noted of all of those, all the emitters, but the point was that it's significantly different.
Yeah. And you're using the term emitters, is that?
It's by emitters, I mean a source that should fall under. I like how Brian just said.
I did.
He's noticed that. Yes, sir. A potential emitter, a potential source that falls under a specific emission line. So it could be H alpha, which is set redshift of around 1-ish.
In this case, very much one. Yeah, so we're looking at H alpha right now, but we're looking much redder, and so that means higher redshift. Right?
Yes.
So here you're looking
Specifically here is around 1. And the O2, O3 doublets, I believe, which is O2 is about 2.42 to 2.53, about that range.
give or take. Yeah.
Give or take, I kind of did, I'm saying those numbers because that's what I did for my data set at least.
Yeah.
And then O3 being around 1.6.
Yeah.
So far this isn't the only image, we've done this to 2 other pointings or images. I can bring this up as well if you'd like.
That'd be great to see maybe one more. And then how does this fit overall with the research that you all are working on together?
Yeah. So while you're bringing it up, I can talk a little bit about
Please.
it.
Because this is sort of a different instrument, so I mean, because the data is different, right?
It is, yeah, but the concept is very similar, and so this particular set of observations is targeting another really massive structure in the early universe. This is the Hyperion proto-supercluster. This is the one that we featured in other sessions. And this is a structure that, is measured to be about 5 million billion suns.
5 million billion. I just want to make sure that we state that clearly. Amass 5 million billion times that of the sun.
Yeah.
And just for context, our Milky Way galaxy is something like 100 billion.
Really?
Yeah. So it's
Wow.
hundreds if not thousands of galaxies and a lot of dark matter, a lot of gas. This is a system that we detected in galaxies. It was also mapped by this LATIS survey, and they found a very high concordance between the galaxy overdensity and the gas overdensity. And so this is one of the systems that kind of follows what I would think of as kind of a canonical relation, or like falls within my naive expectations of matter attracts matter. If you have a bunch of gas sitting around in the early universe, it's probably going to form galaxy stars and then galaxies. And so these images are of different subcomponents of this system. And we know that there are galaxies there. And so we're trying to basically find as many galaxies as possible. And then Joel's attempting to construct something called a luminosity function. Like, if you want to show, talk about that or anything.
I can show that as well, but I was going to show the third pointing as well.
Sure, yeah. So this is just a different part of the Hyperion.
Yes, it's a different part.
It's enormous. It's on the sky. It's maybe a quarter of a full moon.
That's quite
it's not small.
So for reference, this J-band image is a small section of a larger master J-band image, which Lou so graciously cut out for me. I have my own code that they would cut it, but this was a much better job. So what was done is that it was cut out to fit an approximate area of each pointing. So what we saw as the first image was the first 2 pointings that were kind of, I guess, meshed together, right?
Yeah. They kind of stitched together.
Yeah. And this is the third pointing. There's the fourth one as well, if you'd like to see it.
So this third pointing with the all the blue dots.
All the blue dots are potential emitters.
Those are potential emitters. And why are the others not potential emitters?
Do you want to zoom in and like blink?
Let's go.
That one.
This one. So if you look at the surrounding area, that a lot of the surrounding area loses a lot of its
It shrinks
flux of
up.
value. It just shrinks up, whereas these set emitters, or a good portion of them, tend to still retain a good portion of the value,
I see.
like right here,
Okay.
bottom
That
right
is-
of the image.
Oh,
Look at that, relatively nothing.
and then,
It's a little bit off center, but
let's see.
it's significantly larger.
Wow.
So the goal is to make sure that their relative flux is positive,
Mhm.
or not positive, but greater than the relative flux in the broadband image.
I see. And you're doing this visually.
I'm doing this is after the cuts are made, after the initial set of emitters are made. This is just a visual test to see if what was coded is actual reality for another.
So you're doing mathematical operations, right? So you're doing mathematical operations on the various images. You're basically subtracting off the brightnesses from one another. Like,
Yeah.
it's nothing much more complicated than that. And so that would tell you red or blue. If there's excess of flux, then it's red. If there's decrement of flux, then it's blue. And so it's just another way of saying it's shining more in this image than it is in the other image. And that's a very strong indication that there's some sort of one of these emission lines, these recombination lines that are sitting right in the middle of the filter. And so, you know, you can imagine that trying to understand how far away an object is really difficult.
Yeah.
But once you get one of these you see evidence of line emission, there's only certain lines that emit very strongly in galaxies. So like Joel mentioned, singly ionized oxygen at about 328 nanometers, doubly ionized oxygen emission at about 5,000 or 5,000 angstroms, 500 nanometers. And then hydrogen alpha is another one. It's like Lyman alpha, but different energy levels. And this is at 6563 angstroms, so 656 nanometers. And so you go from, I have no idea, basically no idea how far away that galaxy is, to, well, it's one of these three or one of these four. And so you've now taken every possibility, collapsed it down to 3 or 4 possibilities. And then you can augment that with statistical information, which is in fact what Joel's doing here in Hawaii, and far beyond taking the observations. Ben and Joel are working on a statistical model that's going to combine together probabilistic information from all different broadbands with this information, and then construct a something called a luminosity function of galaxies, which tells you it's a glorified histogram. So basically, you just count the amount of emission that's happening at different brightnesses, and that will tell you something about the properties of the galaxies in that system. So hydrogen alpha emission is a direct proxy, near direct proxy, for the amount of stars a galaxy is forming. There's some assumptions that go in there. What we call metallicity in astronomy is one of them. So how much heavier elements there are relative to hydrogen and helium, how much dust is present in the galaxy, because dust can extinct some of this light, redden it basically, and turn it to the IR, further in the IR. And so you have to make corrections for this. But once you do that, you can say, I see that this galaxy is emitting Lyman alpha or hydrogen alpha or whatever at this level of brightness. I can, through physics and mathematics, convert that to the number of solar masses per year it's forming of stars. It's pretty incredible, because stars are born in these cocoons when they young. The O and B stars, the very bright, massive, hot stars, they ionize the surrounding gas, and then these recombination lines, which is how they're defined, appear as the hydrogen cloud, the nursery is ionized. and then recombines. So, we're looking at the number of stars being formed in these galaxies in this structure, and then we're going to compare that to other structures. And so one can imagine if we have a system where there's a lot of gas, but not a lot of galaxies, well, not a lot of stars are being formed because stars make galaxies.
Yeah.
And so a luminosity function in a system like that would look very, very different, presumably from one that is kind of more normal, even if it's still very massive. And so the ultimate goal is to compare and contrast these luminosity functions. This is our metric. This is our measurement that we're going after between these different systems and see, okay, is it different? Yes, it is, or no, it's not. If yes, what are the different properties of these different systems is there some sort of, first, is there some sort of correlation? And then what would be the causation for this correlation? I can show just a couple of things before I think we're right at the end here.
I was gonna say an example of like the luminosity, right? For example, the solar luminosity is about 10 to 36, I think. With,
Solar.
or ergs per second.
Oh, I put me on the spot.
That's what I think, yeah. It's.
I haven't thought about it in a long time.
Okay, I'm saying it's,
That was
the
fun.
average galaxy should be about 1,000,000 times brighter than the sun.
The average
Yeah,
galaxy.
the average galaxy in our selection at least,
Oh,
should be about 1,000,000 times brighter. So I think that solar luminosity, since all this should be in
Ergs per second,
ergs
yeah.
per second, yes, so it's 10 to 42 versus 10 to 36. That's.
Okay, I don't know I know the mass of the sun in kilograms. I don't know the luminosity.
9,
1.99 absolutely.
yeah.
Two. That's it.
Two.
I go two.
Could be, yeah.
wow, that's incredible. And so you're working on this now. Will this, and I know you're visiting Hilo to work with Finn and Roy and Brian, the rest of your collaborators on this. How long will this portion of the research that you're working on take you?
The data analysis, that's I honestly don't know about how long it's gonna take me. That all depends on, I guess, progress per day, but it's just, yeah.
You're making good strides. I mean, you've been working for about a year?
About a year, yeah. First
Um,
couple months, I mean, talk about horror stories, I couldn't even get a couple important programs on my computer.
Which we deal with a lot of antiquated software.
Yes, so I had to like reset a bunch of things on my computer. I had to reinstall the main coding software that I use, Python, Anaconda, about 4 times, I think. And then we finally got it to work in like November. And that's when we started to make the initial figures. And since then, I've been trying to make as much time as possible to work on this.
Yeah, we're making huge
Yeah.
progress now. I mean, you've basically self-taught the code. You're now making cuts. We still have clearly work to do with the analysis, but you're already starting to write the paper. So we're starting to talk about the final stages, which is the Monte Carlo portion to create the luminosity function. Read in ancillary information like the statistical modeling from the Cosmos 2020 data set. So I mean, you're already making huge progress. Even since you've been here in Hilo, but it's been like 3 days, you've made a huge amount of progress. So yeah.
And the writing is, it takes a lot longer than I initially thought.
Oh, yeah.
Like, yeah.
It doesn't get any faster with seniority either.
I was spending hours and I was like, God, this is only like a page and a half.
Oh, page and a half is already a lot.
That's a lot.
Yeah.
Wow. Congratulations. That's fantastic. We look forward to certainly having you on more Shadow of the Scientist sessions so we can follow your progress. And Brian, I do realize we are just a little bit over our time, and I didn't notice that till you said something, so thank you.
Yep.
But you were going to wrap us up with something a little bit different, I think. You're going to show us something.
Yeah. New medicine. So I just wanted to, well, a couple things.
So
Thank you, Rob. Thank you so much, Rob. It's always wonderful to have you with us. We appreciate you so much. And Bonnie and Michael and Roy, of course, too. And those of you, I see that we had 5 people at last time I checked on watching us on YouTube. Thank you so much. We're going to wrap up here in just about 2 minutes.
Yep. So I just want to play one set of frames. This is taken from our MOIRCS run, so same instrument in November. This was with Taddy Kodama. This was during the session that we had bilingual, the first Japanese session, bilingual Japanese session. And this is the same type of thing that Joel was showing. So this is blinking in between the broadband and narrowband. And I can make this a little bit bigger.
We have not, but I think Brian's going to. We'll know that. You see the image. Also,
And this is in the center of another cluster, even more distant cluster. And so the frame with the streaks in it, that's the one from MOIRCS. This is a quick reduction. So there's some artifacts in it, but that doesn't really matter. The point is, if you look at the sources that are circled in red, the non-streaked image is the broadband image. The streaked image is the narrowband image. You just see all these things just popping out like this huge grouping of galaxies here, this one here, all of these down here. They're just like shining like flashlights. And this was the bracket gamma filter. And so we were looking at redshift 3.3. Again, we were looking for I think we were looking for O3 emissions, so a doubly ionized oxygen. And yeah. Oh, we're about
Yeah, I was gonna say setting for 5, that gets us to like 53. It's 6
and to 6. Okay, yeah, right. So this is like the kind of ultimate goal, and this is the heart of this is the central regions of this protocluster as we mapped it. So this forming cluster, and it turns out there's just tons of galaxies there, and even though we've done all sorts of observations of this structure, even in just this single shot, we found more galaxies than we had found prior. So that's incredible. And then I just want to show really quickly a raw frame. I know this is going to be a little bit of a letdown relative to what I just showed, but so it is. Astronomy is not all pretty pictures.
That's true. That's true.
Okay, so this is on the actual operations machine right now. I'm showing the screen. This is actually a mirror of what they're seeing up at the summit, but I'm allowed to control here at the base facility. And so I'm just subtracting off the last 2 frames. And so the sky is so bright that you actually have to subtract off 2 frames from one another. So an observation, then we move the telescope a little bit, which apparently moves the sources in the sky, and then subtract off the 2 from one another. And so you can see in this image, you have a negative from where the source is in one exposure and subtract it off, and you have a positive over here. And so this is 2 images combined, 2 3-minute images combined, and we're building up 46 images.
46 3-minute.
Yeah, 46 3-minute images all together. And so we build up signal over time. But we do it very gradually like this. And so these are just some of the brightest sources. So this is our broadband image that we're using as kind of a finder on the sky. And so it's, these are equivalent to these types of sources here. This is actually taken from the Canada-France-Hawaii telescope, but this was hundreds of hours probably on the Canada-France-Hawaii telescope. And so these are just the brightest sources. So these help us understand where we are in the sky. I can actually do some analysis on this. So this is, I can look at the contours, the profile of these objects. Some of the fainter ones are going to look a little bit more funky.
What do those contours tell us?
So these are called isophotes. These are lines of constant brightness. And so you can see this one is like skewed a little bit. It looks like maybe it's about 30 degrees. If we consistently saw this over the field, so if I went around like this and I saw it everywhere, that might be an indication that we need to focus again. So this is a way of monitoring the observations. I can also do like a radio cut. So I can look at something like that. And this is azimuthally average, so it's basically doing the starting from the center, the light center, and then it's making measurement at different locations at further and further radius. And then it's plotting like a scatter plot, and then it's doing a fit to it. And so this fit down here, this is the size of this, what we call the seeing cell. So basically how much the atmosphere is blurring out, the optics in the atmosphere are blurring out a star. And so this is 4.51. Always have to have units as pixels. So a pixel on MOIRCS is 0.116 arc seconds. And so we're about 0.5 arc second seeing. So it's half an arc second, which is actually in this band is probably average for Maunakea, but again, yeah, 0.5. But for almost any other site in the world, this would be absolutely spectacular. So
Yeah.
we'll leave it at that. Yeah, the clouds have been kind of in and out. We were enjoying a pretty cloudless night for a while, and then it's been said about 10:45, clouds came in and they're now starting to mess with us a little bit. So, but we got good seeing, and luckily it's only increasing the background by about 20%. So. Yet we persist.
Yes, we do. Yes. Just as you said, Roy, just as you said, we are persisting. They are going to persist. Roy, could you close us out?
All right, well, I want to thank those who've joined us. I see some familiar names and faces there. And, the clouds coming in is a perfect analogy. We are at the whim of Mother Nature here. So I just hope our photons keep coming and we find some interesting discoveries. So in a year or 2 years, you can look out for the papers that that Joel will have written all about what he's found.
Yes. Right, Joel. Well, Roy, thank you
No
so
pressure.
much. We will look forward to that.
Thank you, Roy.
We would look forward to that. Roy, Brian, Finn, Joel, thank you all so much for letting us shadow you as you are working here, remotely for Dr. Roy Gal, but for everyone else here, right here in the Hilo Base facility. In the Hilo Base facility, and Kentaro at the summit. Kentaro, thank you so much for all of your contributions during the session.
Yeah, you're welcome, and thank you all. Thank you giving an interesting talk on shadowed universe.
Yeah.
Thank you.
Wonderful. And we will end it there, and we will see you all next time on